Hello everyone, my name is Yixuan. Today I'm going to share my project titled Transformer-Based Detection of Obstructive Sleep Apnea Using ECG. Let's start with a quick background on what obstructive sleep apnea is. Obstructive sleep apnea, or OSA, is a common sleep disorder. During sleep, the airway can become blocked. This causes breathing to slow down or even stop for short periods. As a result, oxygen levels drop, sleep quality gets worse, and the risk of heart problem goes up. The gold standard for diagnosing OSA is a test called polysomnography, or PSG. It records breathing, oxygen level, snoring, sleep stages, and heart activity using ECG. However, PSG requires complex equipment and usually an overnight stay in hospital. And another option is ECG monitoring. It's cheaper, easier, and even be done at home. With wearable devices like the Apple Watch, it makes ECG a very practical option for large-scale OSA screening. This slide shows the dataset we used in our study. It comes from the PhysioNet Apnea ECG Challenge 2000, which is a public medical signal database. The main goal of this dataset is to help develop methods for automatically detecting OSA from single-line ECG. There are 70 overnight recordings in total, each lasting about 7 to 9 hours. For the training set, we have 15 apnea recordings, 5 borderline, and 15 control. The ECG was recorded with a single line at 100 Hz. Experts gave apnea or non-apnea levels for every minute. These levels were based on measurements of breathing and oxygen levels. This slide shows what normal breathing and heart activity look like during sleep. In the upper part, we see the respiratory signals from the nasal, chest, and abdomen. They all follow a smooth, regular pattern. The blood oxygen level, shown as the black line, stays high and steady throughout. In the lower part, we can see the ECG signal. The heartbeats are evenly spaced and constant. Overall, this is what healthy sleep should look like. Now, let's look at the contrast. This is what happens during OSA. At the top, the breathing signal becomes unstable, and you can see the yellow and blue lines, the chest and nasal signal going out of sync. As a result, the oxygen level starts to drop, and you can see the black line slowly going down. And in the ECG, the heartbeat pattern becomes uneven. Look at around 130.8 minutes. The heart rate clearly speeds up, which could be one of apnea events we can detect in our study. Compared to the previous slide, this clearly shows how OSA disrupts breathing and heart activity. This picture is a typical ECG waveform showing one heartbeat. The large spike in middle is called the QRS complex, and the time between two R peaks is called the RR interval. By measuring how the RR interval changes over time, we can get heart rate variability, or HRV, which reflects how the nervous system controls the heart. Here, we have 3 common features used to describe HRV. So first, let's clarify a key concept. As we saw in the previous slide, the time between 2 R peaks is called an RR interval. In this picture, we can see 3 RR intervals. And an NN interval means the time between 2 normal heartbeats. It means abnormal beats are excluded. The first feature, mean NN, is the average time between normal heartbeats. And then the SDNN shows how much this NN interval vary overall. It reflects the total variability in heart rate. RMSSD measures how much the interval change from one beat to the next. It shows short-term fluctuations. PN20 and PN50 means the percentage of neighboring NN interval that differ by more than 20 or 50 milliseconds. Together, these features describe how heart activity changes over time, especially during sleep. In my study, I used the transformer model. This method was first introduced in 2017 by Yixuan et al. For natural language processing. Its key strength is the self-attention mechanism, which allows it to capture both local and global patterns in the input. This is especially useful for complex signals. When applying transformer to a signal like ECG, we need to make some changes, and there are two options. First, we add 1D positional encoding. It can tell the model the correct time order because ECG signals depend on timing. Second, we can use hybrid models. When CNN layers first find local patterns, like QRS complexes, and then the transformer looks for longer-term patterns. And in my study, I used the second approach. Lastly, transformer works very well on large datasets, but they can sometimes overfit when the dataset is small, so careful tuning is important. In this project, I adopted a hybrid CNN transformer model based on the work by Liu et al. In 2023. First, CNN layers are used to process the raw ECG signal. They help capture local features like QRS complex, which are important for identifying heartbeat structure. And then the transformer takes these CNN extracted features to learn long-range dependencies. For example, how patterns change over time. This combination works very well because CNN focuses on short-term local patterns, while the transformer brings in global context with self-attention. Together, they make the model both detailed and context-aware, which is important when analyzing complex biosignal like ECG. On this slide, I will outline the main steps of our research workflow. First, we segmented each overnight ECG recording into 1 minute windows and extracted HRV features for each segment. For the data splitting strategy, we use group K-fold cross-validation, grouping data by subject ID. This ensures that data from the same subject is never in both training and dataset. It can prevent data leakage, and this is a common practice in biosignal research. Finally, we train the models use either HRV features or raw ECG segments to classify apnea and non-apnea. Here is detailed training and evaluation workflow. I tested a range of models, including random forest, logistic regression, SVM, MLP, CNN, and transformer models. And these models were trained using two types of inputs, 1 minute and 3 minutes ECG segments, or 1 minute and 11 minutes HRV feature sets. For hyperparameter optimization, we use opportunity with K-fold cross-validation and grouping by subject ID to avoid data leakage. Each trail was trained for 20 epochs, and the best parameters were chosen based on the FE score. Once the optimal parameters was identified, we performed final model training on the full training site, and we can check the loss curves to make sure the model had finished learning. Finally, I tested on the official test site, compared with the official answer, and recorded metrics to show on the next slide. In this slide, we compare the performance of different models using 1 minute HRV features. The first 3 rows show traditional machine learning methods, and the next 3 rows show MLP, CNN, and transformer. These 6 models' performance are very close, which suggests that with short HRV windows, the transformer offers no clear advantage over simple models. Here we look at a model with longer HRV windows. Extending from 1 to 11 minutes improve performance from both CNN and transformer, but the difference between them is still small. For raw ECG, accuracy also increased with a longer window, but again there was no clear gap between CNN and transformer. To conclude, the short input window may limit the transformer's strength. And in our experiments, CNN and transformer showed comparable performance. The limited size of the training set may also have prevented the transformer from reaching its full potential. For future work, I plan to increase the training data size, for example, by continuing experiments with the official test set. I will also explore longer input window and self-supervised pro-training to make better use of transformers capacity.